the idea here is if we have a curve and we want to find the length of it, it's not as simple as just taking a ruler and measuring it like it is with a line segment, but we're going to have to use some tools that we learned in geometry and combine that with calculus to find. Let's say we have something like the sine curve here. If we wanted to measure something like this physically, we would have to maybe take a piece of string and lay that piece of string as closely as we can to the curve, and then straighten the string out and measure that using a ruler of some sort. What we're going to do here is we're going to learn how to use the integral to find that length, whether it's the sine curve or any other curve. We can actually use this process to find the length of a line segment also if we wanted to. And it would be an alternative to the distance formula, although it ends up looking just like the distance formula in that case. What we do to find the length of an arc or the length of a curve is we break it up just like we did before. If we were finding an area, we would break it up into separate rectangles. What we're going to do here is we're going to break a curve up into separate segments. We know how to find the length of any one segment, right? Like, let's just choose this segment right here. I'll highlight that one. How would I find the length of that segment? Well, what would I need to know to find the length of that segment? Yeah, if I know the endpoints, the coordinates of the endpoints, then I could use those to find the length of that thing. And essentially what I do to find that length is, if you remember where the distance formula comes from, we make a right triangle and we figure out how much the x value changes and we figure out how much the y value changes, and we use the Pythagorean theorem. You guys remember that? So just for the purposes of this, let's just call this delta x, and we'll call this then delta y. So then what is the length? And I'll call this L. How do we find the length of that, just that segment, just that part of what we're trying to find here? Yes, good. So we need to square both of these. So delta x squared plus delta y squared. The way you would have seen this in a geometry class is x2 minus x1 plus y2 minus y1 squared, obviously. So the distance formula can be written like this using our delta notation, our difference notation. What happens here is if we do this over and over again with a bunch of delta x's and a bunch of delta y's, what we're going to end up with is adding a bunch of these up. So the total length of the curve, or at least the approximated total length of the curve, would be all three of these added up, and we would have three of these things. So we would have a sum, in this case a sum of 3 square roots, but we would have the sum of the square root of delta x squared plus delta y squared. Now, this sigma here tells me that we're probably going to be getting into what? An integral, right? This is starting to look like a Riemann sum. So what we're going to do here is we're going to make delta x really, really, really small, and eventually when the delta x gets small enough, we're going to call it dx. And when delta x gets really small, then the delta y's are also going to get really small, and that's going to go to dy. And I'm doing this very informally. This is not a formal proof of what we're going to do here. I'm skipping a lot of things and leaving a lot of important math out. But what we end up with is something that looks like this. And actually, I should get rid of the sigma, because when we let that go to 0, when we let the width of the segment, or the interval go to 0, it ends up being an integral. Now, like I said, I just skipped over a lot of stuff to go from here to here, but that's kind of the gist of it. That's kind of an informal way of thinking about what's happening. So if we break this up into more and more segments, and those segments are getting smaller and smaller, and we're adding them all together, what we're going to end up with is an integral of this. There's a couple problems here, though. The biggest problem is we're integrating without respect to anything. We don't have a differential here. That's a big problem because we can't integrate without knowing what we're going to integrate with respect to. So what I'm going to do is a little bit of a mathematical trick. I'm going to integrate with respect to x, and I'm going to divide by dx to account for that, to balance that out. Now when I do that, I want to simplify this part, the integrand, as much as I can. So this right here is the integrand, and I'm going to simplify that. And the first thing I'm going to do to simplify that is rewrite this as the square root of dx squared. Again, this is kind of just a mathematical trick here to take care of that. But what we end up with then is the integral of the square root of dx squared plus dy squared all over dx squared. And what can I do to simplify that? This is with respect to x, by the way. How could I simplify this right here, this square root? So this, if I take dx squared divided by dx squared, as Alec suggested, we get 1 there. So this is going to be the integral of the square root of 1 plus dy over dx squared. So we're doing dy squared over dx squared is going to turn into dy over dx quantity squared. And we get this. Now, this integral is actually almost exactly like the formula. What is this right here, dy dx? It's the derivative of y with respect to x, right? So to find the length of this curve here, what we're going to end up doing is taking the derivative and plugging that derivative in here and evaluating this integral. And our limits on that integral, as you might expect, would be a and b. As long as this is a smooth curve and the derivative is continuous, this formula right here is going to work. It's going to give us the length of the curve. Now, I'm giving you two formulas here. You'll notice that one of them is with respect to x and one of them is with respect to y. They're very similar formulas, and it's just telling us that for a particular function going from the point AC to the point BD, we can find the length of the curve two ways. We can integrate with respect to x from A to B, or we can integrate with respect to y from C to D. The only difference is when we integrate with respect to x, we take the derivative of y with respect to x. If we integrate with respect to y, we have to take the derivative of x with respect to y. So we have to take the derivative in the other way. One other thing we need to mention here, to find the arc length of a function with non-differentiable points, so if the derivative isn't continuous or it's not differentiable, what we can do is we can split it up into parts. So if we have a curve that's not differentiable, say at a point like this, so we have a cusp there, what we can do is just integrate the two parts separately. So if it's not differentiable at C on the interval, then we just integrate from A to C and evaluate that integral, and then integrate from C to B. I don't think this is something you necessarily need to write down. You just need to understand how it works. If you don't split it up, what's going to happen here, if it's not differentiable, is your integral is going to blow up. Depending on whether you're doing it analytically or, yeah, just like that. No, never mind. Depending on if you're doing this analytically or if you're doing it on your calculator, different things might happen. If you try to find the length of a curve that's not differentiable at a point, your calculator might give you an answer. Rarely, it could give you an answer that's right, or at least close to right. Depending on how your calculator works, and you guys have different calculators in here, it may give you some type of error. If the derivative is equal to 0, then, if the derivative is undefined because you divide by 0, then it may give you an error because of that. So it's important to know what's happening there and know how to fix it, or if it can be fixed. And we'll look at a couple examples here where we'll deal with that.